fast chemical reactions happen. Right? Why do we care about how fast they happen? Right, well, we could walk through your education process. What's your number one thought process when you came in and started listening to me talk? Right? Or we can rewind to 2 days ago, and 60 minutes into that syllabus talk, what were you waiting for? When does Mike stop talking? Okay, when can I leave? When you walk in the lab room, what's your first thought? When can I leave? This isn't a student-centered or student-specific emotion. This is an emotion that all chemists and people have as well. So when we're looking at trying to design chemical reactions, we want them to happen faster so that we can be done with it and move on to other parts of our lives. Everybody has that same feeling, so that's one of the things that we'll try to do. So if we understand how fast they are, okay, number one, that could be something, okay, let's do that reaction because it's fast. Or, oh, dang, that's way too fast, let's slow it down a little bit. Okay? The other part that moves into it is how can we make it more efficiently? How do we use our time wisely to ensure that we can make that reagent as fast as possible so that it can get used by somebody else, so that I can get out of the lab, so that I don't have to keep talking about the material, right? Right, so we're talking about how we navigate that efficiency. This is a fun little picture of somebody twiddling with an industrial process. Okay, what do we do with all these things in chemical reactions? Anything you interact with, okay, more than likely in your life has passed through chemists' fingertips. Right? You can look at drugs, candies, shoes, phones. Chemists have been involved in all of those stages, trying to figure out what those chemicals are, how do we mix them, what are the best ratios, all of those different systems. Okay? And again, how do we maximize our efficiency behind that system? Synthesis is the big thing that chemists will try and go through and do. Synthesis is a way of making something. Okay? When we go through and talk about 151, you looked at a bunch of different chemical reactions. Okay? Sometimes those chemical reactions were straightforward. We talked about a synthesis. Theoretically, you talked about a synthesis where you took two reactants and you put them together and you made one product. It's a real straightforward combination reaction. Right? But we could run other chemical reactions. What chemical reaction are we looking at here?
Combustion reaction of methane.
Okay, a combustion reaction. Is it of methane? Well, what is methane? Anybody know what methane is?
It's beyond just being a flammable gas.
Yeah, like what is the identity of methane? That's fine, you don't have to know that. CH4, it's one carbon. Does that say 1 after the C? It's an X. What does that mean? It could be anything. So this isn't necessarily methane, but it's some kind of organic compound because it's a combination of carbons and hydrogens. Okay? That could be octane. Why would octane be important?
Because it could produce a greater exothermic reaction.
Well, why do I care? Why is burning octane do anything useful?
Well, if you needed a more efficient fuel, you could use octane over methane.
How did you all get to campus?
With a car.
What kind of car?
Yes.
What was the gas?
Octane.
Octane. In most cases. Okay, other people may be using other sources, but this is one of the reasons why you can go into your gas stations, they'll have octane labels or octane ratings, because they're talking about 8 carbons in a chain. Okay? The higher the purity is of that system, the better the efficiency of that burning process, right? Which is why you can pay more for premium, because theoretically they're purifying it more. Okay? Theoretically. So if we're looking at a synthesis, we could be like, well, in this case, I want to synthesize carbon dioxide. I have no idea why we want to do that. I think that's a bad idea, just for the record. We already do it enough. Okay? I could be like, oh, let's make carbon dioxide. I will also make water in this process, but this could be a synthesis reaction for that carbon dioxide. Okay? And I could look at the efficiency of it, the speed of that process. Is that a good way to go through and make it? Can I do it other ways? Okay? Typically, what are we trying to do with carbon dioxide? Are we trying to make it? And no, we're flipping it. We're trying to actually do the opposite of that. We're trying to get rid of carbon dioxide. Okay? What we've seen here is a process to go through and make one of the most common chemical in the world, which is sulfuric acid. You get more sulfuric acid produced every year than any other chemical. Sulfuric acid is extremely versatile as a reagent, and so it gets used in lots of different places. So we could look at that process and think about the kinetics and the speed of each of those individual chemical reactions and how could we optimize them to ensure a faster production of it, if we know the how that reaction happens. If we don't know the how, we just put stuff in and it happens, that's really hard to optimize anything on. So we want to go through and study those chemical reactions and kind of come up with more principles behind them. Whoops, so I was drawing. So we can look at more examples of chemical reactions, reactants before and products after. We've seen that with our general chemical reactions, but it's similar to looking at things like baking. Okay? How do you put together the ingredients to get cookies? What are you doing? What is the process? All those different stages along those way. How can you increase the speed at which you make cookies? If you've never been a prep chef before, okay? You prepare all your ingredients ahead of time, already pre-measured, so that it's easier to go through and do the mixing process. Not sitting there, well, now I'm going to measure this out, now I'm going to measure this out. You want it already ready to go, so it's faster to make. Okay? We can do similar types of ideas and concepts when it comes into chemical reactions. Anybody know why there's a fire extinguisher there? I genuinely don't know, actually. I haven't had a chance to look into it yet. It is quite possible this reaction is extremely exothermic. And if it's exothermic, it's going to produce a lot of heat, so we could have a combustion issue to worry about, a secondary combustion, so we might want a fire extinguisher. I don't know. Okay. And I don't think it's used in the fire extinguisher. Why do we think it might not be used in the fire extinguisher? Because what do, I turn on the fire extinguisher and it sprays something out. What do you think it's going to spray out, the reactant or the product? Product. Why do you think the fire extinguisher is not spraying out those products? What is HCl? Hydrochloric acid. Do we really want hydrochloric acid spraying out of our fire extinguishers? Okay. Generally speaking, that's probably not a good idea. Okay. Add to that, carbon tetrachloride is also a carcinogen and not exactly something you want to be breathing in either. Okay? So if we look at, and I just happened to see her text, so I understand the cookies reference. Just because we have all those ingredients doesn't mean we know how to actually make the cookies at the end, right? We would need a little bit more context behind it, not just what are the ingredients, which is what we have up top, but what's the order in which we mix the ingredients? Does that matter? Has anybody made enough cookies to realize that that matters? Yeah? So what's the best order?
Sometimes people would brown the butter.
Okay.
That's common for chocolate chip cookies. And then you would usually combine the liquids first and possibly add in the sugar with that, and then add the flour next and all the other solids, and then chocolate chips last.
So why? Why?
The chocolate chips is obviously because you want to keep them as chocolate chips. You don't want the stand mixer beating them up.
Okay, so as you go through the mixing process, you don't want to destroy those chocolate chips. So there's a logic and a reason behind a lot of that ordering. How was that ordering discovered?
Trial and error.
Trial and error. And it's not just trial and error, though, because if it's just trial and error, would we know what the proper order was? So how do we know what the proper order was? Someone took notes on what they did and has then shared said notes with the rest of the world. Okay? That's how we know. Okay? That's the progress of science, is that what we have to do is share those notes and share what changes we've made so that everybody else can learn from those same processes or those failures. So if we go through and look at a chemical reaction, right? So this is a fun thing. If we look at this image, we've got, well, we'll call it 4 lines. How many of those are chemical reactions? Yeah, every single one of those is a chemical reaction. How many of those is the chemical reaction? The very first one. How do you know that?
Because you're just showing steps.
How do you know they're showing steps? Be real explicit. It's obvious. It says steps. Okay? Those are big tip-offs that what we're looking at is steps within that overall chemical reaction. Okay? How do we know we're looking at the overall chemical reaction? Sometimes you'll actually see the words overall reaction so that we know the overarching process that's happening within it. Okay? So that overall chemical reaction, we're looking at a sequence of bonds breaking and being made. The order in which those bonds get broken and made is what's known as the how, or the instructions. How does that go through and happen? When we talk about the cookies, we get to experimentally play around with it and decide which one is the best method. Okay? Because what he described was all fun and games, and that was lovely, but I'm probably not going to make my cookies that way. I'm probably just going to throw them all together because I don't want to spend the time, and I don't think it was that much of a difference in value for my cookies, so I'm just going to mix and run. Okay? Do we get that decision with our chemical reactions? No. What we get to do is look at the overall reaction and be like, well, these things happened. I think it happens this way. I think it happens this way. Okay? And so you'll get people yelling at each other about why they think it happens one way or another. Who's right? Whoever yells loudest? I mean, oftentimes, but that's not true. That's how it looks.
Whoever can prove it.
Comes down to the experimental evidence that supports it. So what we would have to do is outline all of our steps, and then we would start to talk about the speeds of those chemical reactions. We could quantify the speeds of our chemical reactions and say what things control each of those speeds. And we could say, my mechanism, my organization of steps matches the outcome of the speed that we see the chemical reaction do on its own. Okay? Chemists take all of those ingredients, put them into a box, and say, go, and then they wait for the ding, they open up the box, go, oh, there's cookies. Okay? What we're trying to figure out is how that happened inside this black box. Okay? So we'll take guesses at it, and then we have to come up with theories to explain it. So if we go through and look at this, our overall reaction can break down into multiple steps. So we get step 1, step 2, step 3. Okay? In the overall reaction, we have reactants and products. We address those. When we look at these individual steps, do we add anything else new into this? Do I add another label? You at least gave me a head shake yes. You may regret it now. What's new?
Label-wise, it's like liquid or aqueous or solid. Not necessarily this one.
Yeah, I would argue all of that was already specified within this. I mean, we could make the argument there was a typo there. That should have a gas next to it. How do you know you have a reactant? It's the left side of the arrow. How do you know you have a product?
Right side.
It's the right side of the arrow. Do we have anything in our steps that does not show up in our overall reaction? Step 1 doesn't show up? Cl2 does. What are you talking about? Okay, so this species didn't show up in our overall reaction. Okay? It's not a product in our reaction. It's not a reactant. Then why is it here?
Because it's needed for the overall reaction.
I don't see it in the overall reaction, so I don't understand.
It's needed into steps 2 and 3.
In steps 2, in 3 too? Yep, and 3. In steps 2 and 3, it is needed for that reaction to progress. It is a reactant in a later step. Okay? Have we seen things that were reactants and products in a chemical reaction before? The other section was all over it, like it was their favorite word this whole week. It was said at least 3 times by students. It was crazy. Begins with a C. Not a dog, but a catalyst. So is that a catalyst? I'm being misleading. It's not a catalyst. Why is it not a catalyst? Because what's a catalyst supposed to do?
Oh, it's start a reaction?
The catalyst starts the reaction. It is a reactant early on, and then it is also a product later on. If we take a look at our chlorine, it's a reactant later on, and it's a product early on. That doesn't match a catalyst. So it's not a catalyst. Do we have a new piece here? Yes, we do. Because this has a new piece, it's not a reactant, it's not a product, it's not a catalyst, we need to come up with a name for it. What should we call it? And don't tell me it's a chlorine atom. What do you want to call it? An intermediate. We have an intermediate along this process. Intermediates will get tricky because as we go through to try and quantify reactions, let's say if we were going to quantify the overall reaction, we could measure out CHCl3 and Cl2 because they were reactants. If I look at step 2, Cl is a reactant in that step, but did I put it there? No, it was a product of a previous step. So do I know the concentration of the Cl? No, that's really challenging. So for this reaction to progress, I'm using a species that I know very little about. I just know that it is present, or I'm presuming that it is present, but I know nothing about its concentration, at least initially. Make sense? Okay. We have a nice little explanation down there for our carbon tetrachloride being toxic. And then a quick glance at the slides again pointed out something else that I forgot to mention to you all, but I mentioned yesterday. Each of these individual steps are differentiated from the overall reaction because they're mechanistic steps. And in general, we add this word elementary. Elementary steps, okay, or elementary mechanistic steps, have different rules that work or function with them than overall reactions. So it is important to know what's going on. An overall reaction just says stuff goes into a black box. An elementary mechanistic step is saying I'm creaming the sugar with the butter first. That was a cookie reference. I figured you would get it. No one else seemed to respond. Okay, does that make sense? You're changing or you're defining what's going on. We now are describing very specific details about that process. Okay? So how would you describe what is happening in each step? What is the intermediate in this reaction? This in blue, to my understanding, her blue boxes are table discussions, so this is for you guys to go through and do. I want you to describe what is happening in each step. This isn't, say, ozone or O3 gas becomes oxygen atom and oxygen molecule. You're just putting words on the chemical reaction. Describe what's actually happening in that chemical reaction. It's a little bit harder. Work at your tables. So with the new idea of saying, let's move beyond what the symbology shows and start thinking about what the symbology represents, if we're looking at step 1, we're talking about 3 oxygens connected becoming an oxygen on its own and 2 oxygens connected. What happened? I broke a bond. Okay. Could we get really obnoxious? Never mind. Avoid that. Let's just progress forward. Okay, we broke a bond. What happens in step 2?
Broke another bond and then 2 oxygens connected to make another O2.
Okay. We broke a bond, again in O3, and then our oxygens connected. When did those 2 things happen? Why did they happen at the same time? Why did it not? Because you said we broke a bond and then they connected. But you're challenging that and you're saying they broke and connected. Very subtle difference, but it's a very important difference. Why are you saying and, not then?
I have no idea. I just thought that
You're like, Mike asked, it must have been wrong.
I'm storing the same stuff.
It's written in the same line. That's how we know they had to have happened at the same time. Because if we wanted them to happen separately, we would have drawn another line. That's how we know. Make sense? So what we're starting to do is think about the how behind this. Is this actually how ozone is converted into oxygen? I don't know. I genuinely don't. Okay? This is a mechanism that describes what is happening. It matches at least that superficial evidence. What I would have to go through and do is now run experiments to test how would this happen. Does that actually match the explanation? Okay? Is there another mechanism that could have explained this? Yes. Give you a hint. It starts with O3. That was supposed to be a joke. It had to start with O3. There was only O3 to begin with. What happened? We made the bond, and we broke 2 bonds. And we did all of those things the exact same instant. That's another mechanism that explains that overall reaction. Who's right? My made-up stuff or what Dr. Schnebler put together ahead of time? I would bet her. I'd actually put lots of money on that. Okay? But that's what we're trying to do when we think about the how behind things, is identify what those changes were and then start to push at it and look at those overall things. Okay? Mechanisms, because what we just looked at were 2 relatively simple things. Mechanisms can get very complicated. Right? Do we have any biologists in here? You didn't want to raise your hand, did you? No. All right. Okay, I'll point over here where it's closer for you. What is that thing? Yeah, they are. Don't worry about it. Right. If you've got to move into a hardcore biochemistry class, what you're looking at there is an amino acid. Okay, I called it histidine in the last class. I'm not convinced that it is histidine because I'm pretty sure histidine has a different structure, but biochemistry is not my forte. Dr. Schnebler would do better at that, but that's why she's put this up here, is that this is a biochemical reaction where we are going through and converting. Where'd it go? I got to see it up high. There it is. We're converting that into that. And actually, we could argue it's here. Reactant into our product. How that happens, right, and officially we kick out another product out over here. How that happens is how the enzyme wraps around that individual molecule and initiates that. That would be the how behind that process. Okay? Enzymes are awesome because they can do these chemical reactions relatively quickly and easily, whereas humans are pretty crude because we just take the stuff, we put it in a brown paper bag, we shake it up and be like, did I make products yet? No, let's try again. Well, that didn't work. Let's throw a spoonful of magic in it and see what happens. Okay? A bit oversimplified, but close. Okay? Biology's spent years developing that brown paper bag to build these systems out for us. So when we think about mechanisms, they aren't always simple and short and sweet. They can be really long, complicated systems. Okay? But what you're looking at in each of those cases is what is exactly happening in that individual mechanistic step. Oops. Okay? So how do we know it? This goes back to our experimental data, okay, and our knowledge of chemical concepts. So all sorts of other pieces are going to come into play. Okay? And the biggest thing that's going to come out of this is how do we quantify what's happening in our chemical reactions? Okay? So we want to look at the speed of the chemical reaction. Okay? A speed of the chemical reaction, what is speed? Any speed. A rate, you just give me a different definition, a better definition, but describe what is the rate. What is my rate through this room? Velocity, okay. Miles.
Acceleration?
That is an interesting rate that I don't want to go into because that's a complicated one. More simply, the derivative of that, I think. Okay?
That's just velocity.
Distance over time. That's a rate. It's any measurement, any unit over time. It's how do we relate those two units. That's it. Okay? So acceleration you could look at as that. What is the time your speed is changing? But it makes it more challenging. All we care about for distance is distance over time. Okay? For a speed someone's moving. But if we're looking at a chemical reaction, if I mix my reagents together and that container starts flying off the table, I'm going to be a little concerned. What are we measuring for a chemical reaction? You could look at heat. Heat's a nebulous concept that we'll deal with when we get into thermodynamics.
Energy.
Okay? We could look at pressure. Kinetic energy is now how it's moving. That gets a bit dodgy again. Okay? We could look at pressure. What changes when you mix your reactants? How do you measure your reactants? Hint, we started the class with this. Concentration. And what happens to the concentration of your reactants over time? It's a little different than dilute because your volume shouldn't be changing. So calling it a dilution is a little bit weird. What's happening to your concentration? The concentration gets smaller, which is where you're getting the dilution from, but dilution is due to the volume getting bigger, not your moles getting smaller. So if we're talking about the rate of our reactants, they should be getting smaller. This is why we would want to know concentration, because it could help us out. Concentration is a way for us to measure the amount of reactant in a given space. You mentioned pressure. Is pressure related to molarity? When you all studied pressure, you had to study some particular equation, right? What was that equation? You just jumped straight the gun. Man. We'll come back to what he said in a second. Theoretically, you looked at PV equals nRT, right? Okay. And if we wanted to know what pressure was, we could isolate pressure by itself. And what was N? Moles. What was volume? Liters. Jumping straight to the gun. P equals mRT. Pressure is directly related to concentration. Okay? So when we're talking about rates, we can do rates based off of concentrations. We can also do rates based off of pressures. Why would we choose pressures over concentrations or concentrations over pressures? When do you measure pressures? When it's a gas. When do you measure concentrations? Careful. Liquids are pure, there's no concentration. When do you measure concentrations? When it's a solution. Okay? So depending on the phase of your system, you're going to change the units at which you will measure your rates. Okay? Not all reactions have known mechanisms. Why not? Sometimes it's a mechanism, it works. We know it works, and we don't care to know how it works. Okay? There's plenty of reactions like that. There's some that we just don't have enough information. There's no way that we could actually design an experiment that would allow us to nail down the exact how of it. So we just give up and say it works, and we move on. Okay? Other times, just people haven't spent the time to study it well enough. Or we don't have the device to measure those concentrations or to see those things happening in real time. Right? Knowing the mechanism is helpful because then it can allow us to tweak things after the fact. Okay? So what is the rate of a reaction? It's how fast it goes. Molecules that react per second. Molecules we don't want to count because how many molecules are in our chemical reactions? A lot. So we don't want to sit there with powers of 10, so we created a unit to make it easier to get rid of the power of 10, and we now have moles. Right? Some reactions are very fast, some are slow. One of the things that can get a bit misleading that we've got to kind of think about is that if we're going to go through and look at a reaction, since we're looking at a reaction, I'll just delete the word. Reaction. We have reactants going to products. How could I measure my products? Concentration, right? Concentration was moles of product, because product begins with P, over liters. But now I want to measure a rate. How do I change this to represent a rate? What do I have to do? I have to bring time into it. And our rates are our unit per time. In this case, our unit is molarity per time. What time unit do you think we want to use? What time unit do you think we would like to use? Right. Depending on the reaction, isn't what we like to use. That's what the reaction's telling us. What do we want to use? There's a suggestion there for seconds. Why seconds? Why not hours? It's not going to happen quickly. Why is that a problem? What was your number one goal when you walked in the door today? To leave. Okay? And if it's taking hours, that's not a very good goal that we would want it to happen. So we're typically measuring these in seconds. Thankfully, science is working with us a little bit on that respect. And usually our reactions are happening much, much faster than seconds. Right? So that would be the rate for our product. Right? What would the rate for our reactant be? Well, instead of it being products for reactants, so the moles are reactant by liters, because we're looking at a concentration change, over seconds. Those look really similar to each other, right? Should they be equal to each other? Why not? So the amount, so what you're starting to think about why they would be different has to do with the coefficients from a balanced chemical equation. So we would theoretically have to take those into consideration. But if I went through and said r and the lowercase r and the lowercase p were 1 and 1, shouldn't these be equal? You still say no. You're just going to dog me all the way through it.
Each element has different weights.
No. Coefficients negate all that. You're right, if it makes you feel better. What's happening to the concentration of reactants? It's decreasing. How do we mathematically represent that? Yeah, the value for that one is going to be negative. What's happening to the concentration of products? It's increasing, which means mathematically that rate will be positive. So if I want to turn these into an equality, what do I have to do? I got to put a negative sign in front of it. Right? Because now the negative will cancel the negative, and this now makes it out to be a positive. I do also have to consider that the unit, moles of R and moles of P, have changed. So I got to go back to my 151 knowledge. Can I convert the moles of R into the moles of P? Yes, that's stoichiometry from our chemical equation. Okay? That minus sign sets that all up, but then the English language comes in and messes with this too. The English language will go through and say, I'm not going to measure the rates of the reactants forming because they're not forming. What are the reactants doing? Disappearing. So when we look at the rate of disappearance, right, that value will always be positive because the English language is telling us that we're looking at the negative direction. You've dealt with your physics classes with directions and vectors. This is all that stuff coming back to haunt you a little bit. So we have to be real careful with what we're looking at and what we're labeling within those terms.
What is it specifically negative enough to set the magnitude of the reaction?
What do you mean?
I mean, like, you put a negative in front of it, why not just, like, go, okay, the magnitude of these are the same?
So we could go through and say the magnitude.
Okay.
I see what you're saying, yeah.
Yeah.
What is that, absolute value?
Yeah.
Yeah. You could go through and do that as well.
Okay.
Though, I've not seen that in a textbook. Okay. So what are some examples of situations where we would care about the rate of a reaction? We can table talk it. I'll make you guys talk to each other first. Should we do that? Okay. I'll give you 30 seconds. Talk to your table. To care about that rate of that reaction a lot. Okay? In the case of the car, we want it to happen pretty much instantaneously, because if we try to ignite our combustion, our fuel, to get the pistons to move, and it took minutes to get the piston to move, how fast is your car moving? Yeah, not at all. Okay? So we want a fast reaction there. So let's look at the combustion reaction a little bit more. What are the products of the combustion reaction? Water and carbon dioxide. Have you seen that formed anywhere else? Yeah, respiration. Okay? For those of people that were in biology, we get cellular respiration, right? What is cellular respiration? Burning. All that comes to my mind is it tastes like burning. Yeah, never mind. C6H12O6. For those biologists, does that help out? Yeah, what are we talking about? Sugar, glucose. Conversion of glucose into H2O and CO2, that's our cellular respiration, right? Okay, what kind of chemical reaction is this? That's a combustion reaction. Isn't that the exact same reaction that's happening in our cars really, really fast? So wait, when we respire, bring in oxygen, and exhale and convert the glucose in our bodies into energy so that we can function, we're exhaling water and CO2, so we are doing a combustion reaction. Yes. Yeah, you are all combusting right now. Welcome to the world. Do we care about the speed of that chemical reaction? Yes. Yeah. Interestingly, we were like, combustion, I want it to happen fast, do you? When the combustion reaction is happening in our bodies, we do not want that reaction happening fast. We want that reaction happening really, really slow. Right? That slower process allows our biological systems to trap that energy, convert it into something else that isn't us exploding. Right? Which brings in another kind of fun word, and we deal with language a lot within chemistry and playing with it, spontaneous combustion. And if we said that we were going to talk about spontaneous combustion this semester, you're probably like, ooh, this is exciting. How many people have just spontaneously combusted? Every single one of you. Every single one of you is spontaneously combusting right now. When you hear the word spontaneous, you think speed. It has nothing to do with speed in the chemistry vernacular. It has to do with, will it happen? And yes, a combustion reaction will happen on its own. Right? That's why eventually we all decompose, okay? Because that chemical reaction will happen on its own. So we do want to be thinking about the speeds and rates of chemical reactions. I got faster today, but not fast enough, I think. Okay? In order for molecules to react, they must collide. Okay? So we talked about this kind of in the human system. We're talking about concentrations. Okay? So not only do we need concentrations, but we also have these other things that we have to consider, like orientation. Okay? So if I take a marker, okay, a standard whiteboard marker, we've got the pen part, right, and the cap. Okay? And if I'm talking about a chemical reaction, what chemical reaction do you think I might be talking about with these two reactants? Capping it, okay, that's a good idea. Okay, so let's talk about the correct orientation. Did I get a product? That's probably because I didn't have enough energy. Was that working any better? No. So it's not just energy that I have to be concerned about, it's also proper orientation. But is it just orientation? No, it's also
Energy.
enough energy, which we're representing as force in this particular case, to actually get that reaction to occur. So we're getting these extra variables that contribute to the rates of our reaction. Not only do we have to have enough of these particles around that we increase the odds of them interacting, we also have to make sure that each of those interactions happens in the right orientation with the right energy. That's really challenging to control. Okay? Think about orientation. To have the right orientation, am I in the right orientation right now to cap my pen? You can't see it, so you don't know. Guess what chemistry is doing? Everything behind its back, and you can't see it. So that becomes this kind of weird unknown variable that floats around on us. Okay? However, that orientation for a given chemical reaction will always be constant. And if it's constant, if we can control enough of the other variables, we can now solve for that constant. Okay. This is kind of the beginnings of collision theory. And beginnings, you've probably talked about collision theory in 151 a little bit? Nope? Okay. So this is the beginnings of dealing with collision theory. When atoms or reactions occur, they must collide, and there's other conditions along with that collision, orientation and energies. So we could look at a more specific reaction of nitrogen oxide. Nitrogen oxide colliding with ozone to form nitrogen dioxide and oxygen gas. Right? If you have the proper orientation, you can exchange effectively the electron/bond to make that bond. But if you change the orientation this way, that's connecting the oxygen to the oxygen. Is that what we want? Nope, which means no reaction. Kind of make sense? Yeah. Okay? So we have to consider that. We'll do representations of those things so we can pick it up. Okay? Activation energy is how we draw out the energy necessary for this collision, an effective collision to work out. So if we were looking at an energy diagram where we had a reaction coordinate, convenient, we've talked about that before, right? And we looked at this reaction, we could go through and simply label this as reactants and as products, recognize the reactants are in their own well. Whoops, reactants begins with R. Products are in their own well. And that for those two wells to connect, we have to clear a barrier. That barrier is the energy necessary to make that into a product. Okay? The peak of that we called the transition state, typically shown, and I know that looks like an F, it's a little sloppy there, a double dagger line with two crosses through it. Okay? That's our transition state. The energy is represented by the height difference between the transition state and our reactant. You'll typically see that drawn in between, and we would call that our energy of activation or activation energy. Kind of, sort of? Cool. Is my drawing correct, generally speaking? Right? We have reactant energy, we have product energy, we have a transition state. Yeah, all that seems to make sense. Do I know where the reactant is with regards to the product energy? Ooh, an aggressive no. Another aggressive no. I'm pointing it out like it's a problem. It's an exothermic reaction. There was more context provided in the question. The question or the original statement says it's an exothermic reaction, which means where are the product energies needed to be drawn? That has to be drawn lower than the reactant, so that the energy of the product minus the energy of the reactant gets me a negative. Make sense? Okay. The aggressive no's absolutely makes sense in a general just here's a reaction. Be careful to make sure you aren't given slightly more information. Exothermic is in reference to our energy. That's telling us the relative positions of our reactants to our products. So what would the energy profile diagram look like for an endothermic reaction? Label the activation energy and enthalpy change. So we've got this chemical reaction within your groups. See what you come up with. I should have paused it. I apologize for that. So we got a weird recording of silence. Right. One thing that can be helpful is to make sure we have identified our pieces. If we're talking about exo and endothermic, how do we determine those values? So yes, exo is negative and endo is positive. How did I get those negative and positive values? What did I have to do?
Enthalpy change?
You just gave me another word. How do I get a negative and positive value? Not yet.
Energy is absorbed or released.
Okay, how did I get that calculation? How am I calculating that value? How do I know energy is absorbed or energy is released? Say again?
Measure the temperature of the reaction.
We could look at the temperature of the reaction. Does this say anything about the temperature of the reaction? No, okay. Need some space here. This is giving us ultimately information about the relative arrangement of our products versus our reactants. And we go through and calculate the enthalpy of the reaction. How do you calculate the enthalpy of the reaction? You look at the product energy minus the reactant energy. And if it's an exothermic reaction, what does that mean? How does it become negative? The reactant energy must be larger than the product energy. That's the only way you get a negative value. Okay? But what if it's an endothermic reaction? Does my equation change? Nope, the equation, it's still calculated the exact same way. It's product energy minus reactant energy. But now I know the endo is positive, which means products must be higher than reactants. So I can go back to my diagram and draw products. You know, let's be aggressive. Let's go really high, and we'll draw our reactants really low. And if we're going to complete out our diagram, whoop, that was a pretty nice curve. Thank you. Okay. That works. There's a whole bunch of different variations that work because we haven't defined what that distance is. Okay? As long as the product energy is higher than the reactant, you're fine. As long as your activation energy is higher than both, you're fine. Make sense? Okay. So, activation energy is necessary to go over and transition from one well to the other well. All right? So it is unstable, it's a high energy point. If we look at a high jumper between this, okay, we can take pictures and imagine what's happening in each of those transitions. But where can we actually say that person is grounded? They are grounded before the reaction, before they jump, and they are grounded after they've jumped. That peak as they're moving through, they're not grounded. They don't exist at that point. They're transitioning from one side to another. Right? So it's a really hard point to kind of nail down because we can't go in and say, what is that point? Let me isolate that and grab that thing. I can't grab it because it doesn't exist. It's a transitional point. Okay? Molecules must collide with enough energy to react. That's our activation energy. Okay? So now we've got a different system. Okay? The activation energy was that gap through. If I want to look at kinetic energy versus my molecules, right, I want to draw a graph that shows the distribution of that energy across our sample molecules. Any ideas what that would look like? Cheat and turn the slides. Because I wish I had a better description for you to help you kind of guide you into that. I don't think I really do. And what I would ultimately do is look at this and talk through what's happening within this. If we look at a random sample, so if we look at the room, okay, we take the people in this room as individual molecules, right? There's a set energy total within this room. And now what we want to look at is how that energy is distributed, kinetic energy-wise, across each of those individual particles. Right? What does that mean? Well, if we look at it, there's some people that will always be not moving. It's always going to be a case. Which means our curve is always going to start with 0 kinetic energy. We're like, well, if there's a lot of heat, wouldn't they always be moving? Except they collide. And in that collision, it may have lost all of its momentum, and it will stop with 0 kinetic energy. Another particle will quickly come behind and cause it to move. So these particles are going to be constantly changing their states. That 0 kinetic energy particle could easily become the highest kinetic energy particle at some point in time. But what we're looking at is a snapshot within that system. Kind of make sense? Right? If we consider the highest energy particles, right, I think we can all agree that I'm probably the highest energy particle in this room. Is there anybody else that is as high energy as me, at least at this point? No, not even close. Right? So the odds that you max and min, very, very, very slim. Right? Small populations. Which is why when we look at the curve, we're coming all the way down to that x-axis. We're saying there's very few particles. Right? But we'll always have at least one at pretty much each of those ends. Then as we increase or decrease, as you want to look at it, perceive it, you're going to slowly move up into kind of a bell curve shape. So even though all of you are sitting, some of you are still moving more than others in any given instant. Right? If you had a partner sitting next to you that was asleep, you might nudge and wake them. They were a 0 and now they've activated. Right? Maybe that took all the energy out of you and now you're asleep. Right? That's what's happening within this. And if we consider what happens for a chemical reaction, the activation energy just happens to be an arbitrary value within this system. Okay? Here we're identifying it, that any particle greater than that energy can now make a reaction. Do you think this would be a good reaction to run? Why not? How many particles are going to make products?
Very good.
Right? And what's the goal of most of our chemical reactions? Make products. So what we might want to do is change the mechanism of how this reaction is happening. By changing the mechanism, we're changing that curve on how it happens, which may very well drop the activation energy. And if the activation energy drops, what happens to the number of particles that can make products? I get more particles in that grayed out section. What happens if I increase the temperature? For most particles, what happens when you increase the temperature? They move more. You get more kinetic energy. You're still going to get that lazy particle that just got hit. Maybe by 2 particles came in and sandwiched it. No, I'm done. Can't move anymore. So you will still always have your curve starting at the bottom. But now if I add more heat, I'm getting more energy. More particles are going to start to populate out this end. Which means my curve is probably going to start to look something more like this. But it's the same number of particles, so it's going to reach less of a max. What does this mean? Higher energy, still more particles, or higher temperature, more particles can make product. They've cleared that activation barrier. Kind of, sort of? Size is number 21. I feel kind of okay about this. Right? Higher activation energy means slower rate, which now brings in this concept of when we look at an overall reaction and its mechanistic steps, it's not just saying here's the steps that we suggest, but we're now also going to bring in this concept of slow versus fast. Right? That added piece of information is now going to change how we would look at this reaction. We'll call this one red. I'm going to do these independent, and we'll see why I want them independent in a second. If I looked at the red reaction that's slow, I might go through and show a wicked high activation barrier. And if I look at the orange reaction, it's fast. What should my activation barrier be? Really, really, really low. Kind of makes sense? Okay. So the last thing, or the thing that we'll end with today, would be that same reaction. No, it's exothermic. But now what I want you to do is draw an energy diagram that represents the overall reaction, taking into consideration that it's an exothermic reaction and that we have these two steps, and the first one is slow and the second one is fast. There are those people trying to quickly go through and do it. That's not what I'm saying because we're done. That's what I want you to think about and process by the time we come back for class Tuesday. Make sense? Okay. And if you got an idea, you can always show me.